Okay, so really what we're doing is we are studying cosmology. Um, and basically cosmology in, if you're a fan of Hitchhiker's Guide to the Galaxy, then cosmology would be exactly what that whole comedic book, sci-fi comedy about either a book or a movie. Basically, it's life, the universe, and everything. And in the Hitchhiker's Guide to the Galaxy version of this story, the ultimate answer to everything is 42. So if you haven't seen that, it's pretty amusing. So, cosmology. Oh, and by the way, I'm inviting you to take notes if you want to get some extra points. You can turn those in when we're done. So, cosmology is the study of the universe. It's the study of everything. Um, the cosmos. So it would include these different components. What is the nature of the universe? In other words, what is the universe? What is it made of? What are its parts? What is its structure? It would include the origin of the universe. Where did it come from? And as you know, scientific evidence suggests that it came from a big bang back here. So here's long ago, 13.5 billion years ago, and here's today. It includes the evolution of the universe. How has the universe changed during its lifetime? So that's what these diagrams are showing, some of these changes. And then, what do we think the end of the universe will be like? In fact, will there even be an end of the universe? We don't know the answer to this question right now. We can make some informed predictions, but we don't know for sure. We need more data. So speaking of data, let's look at what different people have thought about the universe throughout time, and how they've explained the cosmos. So really, science and religion are asking very similar questions about the universe. Well, where did we come from? Where are we going? Oh, things like this. What's the meaning of life? These are questions that people have asked across the ages and across all different cultures. One of the differences between science and religion, the way we ask our questions, is that science really focuses on how things happened. How did the universe form? How did it get to be to the way it is today? Whereas religion tends to ask why questions. Why are we here? What is the meaning of life? That's more of a religion question than a science question. So we are looking at the same things, but kind of looking at them from different angles, from different viewpoints. And of course, that's going to give us different answers that we can combine together, perhaps, to come up with a more complete view. So, as you know, science is going to try to answer these questions using data. They're going to make calculations. They're going to gather information with their senses. They're going to make observations. So that's the science approach. Gather the data, make predictions, test the predictions, conduct experiments, try to focus on what we can actually measure out there. Now, sometimes there are questions that go beyond the data. And if the question goes beyond the data, we cannot give a scientific answer to it, at least not with our current technology. We have to limit our answers to the data and the calculations that are based on data in the first place. So one example of these questions that goes beyond the data is what happened before the Big Bang? We don't have any data. So how could we possibly try to answer that question? No data, we can't even really ask the question. Furthermore, the Big Bang formed both time and space. It didn't only form space, but it formed time, which means there was no before the Big Bang. And this is crazy stuff that we're thinking about today. It's pretty interesting topic, and I hope you hang with me, and I hope that we find it a little stimulating for your mind to consider the possibilities that are out beyond, really beyond the realm of our everyday experience. That's part of what's difficult about this whole topic is when we're talking about the Big Bang, we're talking about a universe that exists in a form completely beyond our ability to figure it out. We don't have any experiences, we don't have any perceptions that can really allow us to understand these things. For instance, what would it be like to be in the middle of the sun? Well, we would be fried in an instant, so we could never experience that really. Um, and then the kinds of matter and space that we're talking about with the Big Bang go even beyond that. I once heard a famous science fiction author, Arthur C. Clarke, said that it's like it's as if we were intelligent fish. So imagine an intelligent fish that asks all kinds of great questions, but this fish has never left the ocean, right? It doesn't have any experience beyond the sea. And so it could have lots of interesting questions and ideas, but it would never think of fire. It's beyond the fish's experience. Fire is something that a fish could never even understand because it doesn't exist in its world. Similarly, that's what we're going to delve into today as we talk about the Big Bang, things that are way beyond our experience. So let's look at the history of this theory. Where did it come from? I think looking at where the theory came from helps us see that it makes more sense than it first might appear if we were just to jump into some of the deeper ideas of it. So before the early 1900s, people thought the universe was infinite, that it was unchanging, that it was ageless. That diagram that I showed you earlier that showed those different stages of the universe, they would have never considered that because it was unchanging. But then Einstein came along, and his theory of relativity showed that our ideas about nature are incomplete. And that's partly just because we are human beings that have this particular body shape, this particular brain, these particular sense organs, and we are not able to experience nature as his theories calculate that nature really is. His most famous idea, of course, was E equals mc squared. And if you don't know what these stand for, E is energy, M is mass, the mass of the matter. C is a constant, and it is the speed of light, 186,000 miles per second. So C is a huge number, but then we're going to square that. 186,000 miles per second squared times the mass in the matter shows the amount of energy in that matter. And I want to focus on the equals sign. Isn't this really saying that energy and matter are interchangeable, that they are different components of the same thing? It's like the front of your hand and your back of your hand. They're different parts of the same thing. They are interchangeable. Energy is matter at this level. Well, that's just the beginning, because then when we get into Einstein's theory of general relativity, it also shows that space is equivalent to time. Space and time are different facets of the same thing. Similarly, gravity is equivalent to motion. There is no difference between gravity and motion. These are crazy ideas. That's why I chose this picture of Albert, because it's just something that tickles our brain. Now, his calculations that led to these theories have provided us with predictions that we can test. And when we test his theories, they generally have been confirmed. An example is one of his predictions, based on his calculations, is that gravity should curve space, which is pretty trippy to think about by itself. Space is curved by gravity. Gravity is a force that bends space, and this in turn can bend light. Well, the only way we have to test this is to have a massive object with a lot of gravity next to a light source, and then we have to look to see if the light source has been bent. And this has been proven correct during a solar eclipse. So have a look at this diagram here. Here's the Earth. And on a normal day, we look out at this star, and it's the light from the star follows this red path, or so we think. Well, this star happens to be in line with the sun, so it's not really visible during the day unless you have special equipment. However, during a solar eclipse, when the moon would be right here blocking off the sunlight, we can actually measure that the star is way over here. And what's happening is as the light is coming towards us from the star, it's falling into this like gravity well that's formed by the sun. The sun has made this deep gravity well. It has bent space and time. It has warped space and time to the point that light falls into it, but it's not as strong as a black hole, so the light can make it back out. And then it appears to follow the same path as what we thought the star was showing us. Notice the Earth has its own little gravity well too, and the moon would have another very small one. But the sun is much bigger, so it has a much deeper gravity well than we do. So the light from the star is bent by the gravity of the sun, and it makes it seem like the light is coming from this red line. That's where we think the star is. This is where it actually is. So this is one aspect of Einstein's predictions that we've been able to test. Another one that was a little, shall we say, more harmful was the idea that we can convert a small of matter into a huge amount of energy, and that resulted in the atomic bomb. So Einstein's theories predict a variety of things that we can test under certain conditions, and they're often shown to be correct, and this includes the idea that space is equivalent to time. And that takes us to the next stage of the development of the Big Bang theory, which was work done around 1920 by Edwin Hubble, and the Hubble Space Telescope is named after him. Basically, he proved that the Milky Way galaxy was only one of many galaxies. Before his time, we thought the Milky Way was everything there was, that it was the universe, and these other little spiral shapes that we see in it were parts of the Milky Way. Well, now we know that those are very distant galaxies, millions and millions of light years away. And we are just one galaxy, one little cluster of stars in one part of the universe. Well, not only did he prove the Milky Way was just one of many galaxies, he also showed that the galaxies are moving. And their movement is all away from us because they all have what's called a redshift. So all the galaxies are moving away from us. Let's look at the redshift a little more closely. So this is known as the Doppler effect. And it works for both light and for sound. Anything that's emitting waves while moving shows this Doppler effect. For light, we have both a redshift and a blue shift. For sound, it's a change in pitch. So for example, I'm going to play this recording. I don't know how well you're going to hear it, but you'll be able to tell because of your daily experience whether this object is moving towards you or away from you. You know if a car is moving towards you or away from you by the way it sounds. The same thing with a jet, which is this recording, and the same thing for a helicopter or uh, a siren on a fire truck. You can tell if it's moving away or towards you because of the Doppler effect. So let's see if you can hear this. So ignoring the woman advertising for the website where I got that free download, you could hear the jet going. But I want you to keep in mind the jet itself is making the same sound that entire time. The car engine makes the same sound the entire time that it drives past you. The same siren noise is being made the entire time that siren approaches and then it leaves. So what happens that makes the pitch change? Well, as the object is moving towards you, the sound waves, or in this case, the light waves, are compressed. They're squeezed together, and so we hear it as a higher pitch. When we're looking at a distant object, the squeezing of the light waves shifts those light waves towards the blue end of the spectrum, where the peaks are a little closer together. On the other hand, when an object is moving away from you, the light waves are stretched out towards the red end of the spectrum, with more distance between each peak. And this is what we call the redshift. And all the galaxies show a redshift, which shows us that all the galaxies are moving away from us. Now let's think about that for a minute. If they're all moving away, doesn't that suggest what they were doing in the past would be the opposite of moving away? Not only are they all moving away, the further away it is, the greater its redshift. In other words, the further away the object is, the more distant galaxies have bigger redshifts, meaning they're moving away from us even faster than the close galaxies. So all galaxies show a redshift. The more distant ones have a bigger redshift. Well, let's back up in time. If everything's moving away right now, doesn't that mean it had to be closer together in the past? And that it's actually the entire universe is expanding? If everything's moving away, that means the universe is expanding. And if it's expanding now, doesn't that in turn suggest that in the distant past, everything was closer together? And before that, it was even closer together. And before that, even closer and even closer until everything was once packed together into a single point from which everything else expanded out of. And that was the idea of the Big Bang. Basically, this fact of the redshift of all galaxies leads to the idea that everything was once in one place and it all expanded out of that. The Big Bang. So here's the raisin bread analogy. Each raisin is a galaxy, and they're all moving away from one another. Just like when you take the dough of the raisin bread, it starts out small and it expands. As the dough rises, it expands, and that pulls the raisins apart with it. It's not that the raisins are getting any bigger. The galaxies are not getting any bigger. They're not actually expanding, but the space between the galaxies is expanding, and it is pulling the raisins along with it. One thing that I think could be improved in this diagram is it shows us in the center, and there's no reason to think that the Milky Way is in the center of the galaxy. In the center, of the universe. So let's look at another diagram. I like this one also because it's kind of got a before and after and some measurements. So here we are, and we measure our distance to these galaxies. And then later we measure again, and we find that they have moved further away. Everything is expanding. The whole universe, the whole loaf of bread, is expanding, and this is pulling the galaxies further and further apart. The galaxies themselves are not expanding. Space-time containing the galaxies is expanding. And notice again that this analogy fits with the idea that the more distant galaxies are receding, are moving away from us faster. So this one has moved another 16 centimeters away, whereas this one has only moved an additional 1 centimeter away. They're moving faster if they're further apart. So this is what we mean by the expansion of space and time, pulling the universe apart and spreading the galaxies further and further away from one another. So a couple things to think about to help you imagine the Big Bang. First of all, it's not an explosion of matter. We're not talking about an explosion here. We are talking about an expansion of all space, and the matter within that space is carried along with it. So not an explosion, an expansion. So maybe bang was a poor choice of words, I'm not sure. An expansion of space. And we're along for the ride. Now, here's the next thing. It wasn't just things that came out of that single point at the beginning. All of space, all of time, all of matter, all of energy, they all came out of that one single point. And they started as the same thing. They were unified in that single point, which is known as a singularity. And this point would have been smaller than the tiniest particle of an atom. Everything in that tiny point packed together, so it would have been infinitely heavy, but infinitely small. And this is what I'm talking about when I'm saying we don't have the ability to understand what matter would be like, what the universe would be like, because we've never experienced anything like this. It's really beyond the realm of human experience. But the data that we've measured and the calculations that we've made support the idea that this is what happened. So just as the center of a black hole is known as a singularity, where all this matter is packed together, it's in a tiny space, but its mass is unimaginable, infinite density. So we think this would have been a pretty good comparison to the early universe when everything was packed together into a singularity. And when I say everything, again, I mean time, matter, energy, and space all in there. Here's the other thing that's hard to think about. The universe did not expand into anything. There was nothing. There was just it. That's what we mean by universe. Universe is everything. It has no edge. There's nothing outside of it. It's not expanding into anything. It's just expanding itself. And again, this is pretty crazy stuff to try to challenge your mind with. I don't know if you're a Monty Python fan, but yeah, this stuff definitely hurts my brain. Okay, then we found some more evidence for this explanation, for the Big Bang. Not only that all the galaxies are moving apart, but also that there is some remnant energy everywhere we look around us. So the first big piece of evidence was the redshift of the galaxies, showing that they're all moving away, that the universe is expanding now, and therefore in the past it must have been smaller and smaller and smaller. The next piece of evidence came from analyzing light waves in the microwave part of the spectrum. So microwave light has less energy than visible light, but it has more energy than radio waves. And so we can set up microwave detectors to measure the amount of microwave coming to us from different points in space. And of course, stars and galaxies release microwaves. But the crazy thing is that these two American astronomers in the 60s were able to measure microwave radiation from between the stars and galaxies. Microwave radiation in empty space. There was no source emitting that light. Not only that, they found that it surrounds us in all directions. We are surrounded by a globe. We're inside of a sphere of microwave radiation. We call this microwave radiation the cosmic microwave background, the CMB. And we think it's a remnant of light given off by the Big Bang. We sometimes call it the echo of the Big Bang. So you could think of this microwave light, the CMB, as the flash released when energy first separated from matter. And that was about 350,000 years after the Big Bang started. Another way you could think about the CMB is that it's heat left over from the Big Bang. Just like you might expect an explosion to give off heat and to push things apart, we can measure both the heat and the movement of the objects as they're getting pushed apart by the expansion of the universe. The cosmic microwave background, again, is in all directions, up and down, left and right, front and back, 360-degree sphere around the Earth. And it is further away than the most distant galaxies, which also means it's older than those galaxies. This light that we can measure, microwave light, is older than the galaxies because it's more distant than them, which takes us to this idea of look-back time that we're going to look at in a minute. But first of all, here's the crazy-looking microwave antenna that they used to discover the cosmic microwave background. And these two guys won the Nobel Prize for their work. So, look-back time. First of all, remember light travels at an incredibly high speed, 186,000 miles per second. The Earth at the equator is about 25,000 miles in circumference. So if you had a bunch of mirrors set up around the planet, you could turn on a light and it would circle the planet more than 7 times in 1 second. That's how fast light is traveling. And yet the distances are so vast in the galaxy and in the universe that we are looking at things way back in time. So light takes time to travel through space. Some examples. The sun is 8 light minutes away, which means as I look out my window and I see the sunlight here, that light that I'm seeing reaching the Earth right now left the sun 8 minutes ago. So if I put a solar filter on my telescope and I look at the sun, I'm going to see it as it was 8 minutes ago. I'm not seeing it as it is now. I'm seeing what the sun was like 8 minutes ago. For all I know, it just blew up, and I'm not going to find out for 8 minutes. Then it's going to get dark and cold awfully fast. The closest star beyond the sun is Alpha Centauri, and it's 4.4 light years away. So that means when we look at Alpha Centauri, we're looking at light that left that star 4.5 years ago. It took 4.5 years for that light to travel to us from Alpha Centauri, and that's the closest star. Traveling at the fastest thing that we know of is the speed of light. It still took it 4.5 years to get here. So when I'm looking at Alpha Centauri, I'm seeing what it looked like 4.5 years ago. So let's see. If you're like 17 years old, that light left Alpha Centauri when you were what? 12 and a half. And it's just now reaching you. The Orion Nebula, a beautiful object in the night sky, 1,344 light years away. I'm seeing the Orion Nebula as it looked 1,344 years ago. I'm not seeing what it looks like today. I'm seeing what it used to look like. How many new stars have formed in that nebula in that 1,000 years that have passed since the light left the nebula? Our nearest galaxy neighbor, the Andromeda Galaxy, 2.5 million light years away. So when I look out at Andromeda, I'm seeing what it looked like 2.5 million years ago. The light left Andromeda about the time that Australopithecus was first evolving into humans. It was way before modern humans existed that light left the galaxy, but it's just now reaching us. The most distant galaxies are called quasars. They're 13 billion light years away. So we're looking way back at time. That's why we call it look back time, because when we're looking at a quasar, we're seeing what it looked like 13 billion light years ago. So the more further back in time you look, the more distance in space you look, the further back in time you're looking. So in a sense, a telescope is a time machine, showing us what things were like in the past. And the cosmic microwave background, 13.5 billion light years away. So here's an example. This is from a website that's called the Atlas of the Universe, and it's showing these clusters of galaxies. These dots are not stars, these are galaxies. This is showing 100 million light year distance to the Virgo supercluster of galaxies. So if it's 100 million light years away, that means light that left the Virgo supercluster is just now reaching us, and that light left the supercluster during the time of the dinosaurs, 100 million years ago. This light was released, and it took 100 million years to get to us. We're part of the local group of galaxies. And vice versa is also true. Light that left our galaxy 100 million years ago is just now reaching Virgo, which means someone with a huge telescope in this cluster of galaxies looking at us is going to see dinosaurs. They're going to see T-Rex and Tyrannosaurus. They're going to see the Earth as it was 100 million light years ago. And it took that long for the light to get there. So the whole point is we're seeing these objects as they were. The telescope is a time machine. We're looking back in time when we're looking across space. The further away we look, the farther back in time we look, and that's what came up with this term, look back time. And this is defined as the time from when the light was first emitted to the time that we actually see it. The CMB, the cosmic microwave background, is the most distant thing that we can actually see. It's almost 13.5 billion light years away. And that means the Big Bang had to occur just before this time. Calculations put it at 13.7 billion years ago. Since I've been learning about this stuff, they've narrowed this time down to a more and more precise number. It used to be that they would give a range of numbers. So when I was first learning about it, they would say the Big Bang occurred between 10 and 20 billion years ago. We're not sure exactly when, but we think it was between 10 and 20 billion years ago. And then they narrowed it down to, oh, now we think the Big Bang had to occur between 10 and 15 billion years ago. Well, today, they've narrowed it down to more of a specific number, 13.7 billion years ago. They have more certainty about when it actually occurred. All right, so we're going to look at a series of little videos by NASA showing some of these concepts about the cosmic microwave background in particular. So here's the satellite that is gathering this information, called WMAP. So the WMAP satellite is way out from the Earth, even beyond the moon. We're going to zoom out now. There's Mars, the asteroid belt, Jupiter, Saturn. We're zooming further and further away from ourselves. Now we're past the Oort cloud, and we're getting out to the other stars in the Milky Way, the clouds of gas and dust that are found in the galaxy. And as we zoom out further, remember we're going back in time also, as we zoom out further, we can see the Milky Way itself, and we can see other galaxies. There's our nearby neighbor, Andromeda. We're still zooming out further and further past all of these other galaxies, further and further back in time and space. There's quasars, very young, powerful galaxies. And when we get past the quasars, we end up seeing this field of light, of microwave light, with these variations in the intensity of the light in different areas that we think could have given rise to the development of galaxies and stars within the galaxies. So let's talk a little bit about the Wilkinson Microwave Anisotropy Probe, which is this satellite that measures the microwave light around us. It's orbiting Earth, but it's at a distance greater than the moon. I think it's at 1 million miles away, and the moon is about 250,000 miles away. But it is orbiting the Earth. And this allows it to detect very faint microwave signals without any disruption from Earth, without any of our, the noise that we're creating, both with our technology and just any natural emissions from the planet are now in the background. And so this satellite has mapped the microwave signals from all around us at high levels of detail in every direction. And these measurements show very slight variations in the amount of energy. And we think that these variations in the amount of energy would allow matter to collapse into the most dense areas to form galaxies. And then stars would have formed within those galaxies. Just like we talked about stars forming from dense clumps of gas and dust, where the gravity pulled everything together into the star, we think a very similar thing happened on a larger scale to make galaxies, where the densest matter collapsed into the center of the galaxy. So here's the photo of our universe. This is our selfie. Universal selfie, the cosmic microwave background taken by WMAP. Just like the globe is showing the three-dimensional surface of the Earth, this oval is showing the three-dimensional CMB surrounding the planet and surrounding the sun and everything. So this is the most distant thing we know, and we can see that it's not an even glow, that there are some areas where the material is more dense and some areas where the energy is more dense. Okay, so let's have a look at another video showing how they got this photo and kind of emphasizing what microwave wavelength light is like. Come on. Okay, so here's our Milky Way, and we're going to zoom in back to our planet in one of the spiral arms out here on the edge. Now, there's the Earth. We're going to look at the view from the WMAP satellite, and we're going to map it. Here we have visible light to start with. We're going to map it in 3D, so we get the entire surroundings. Here's visible light. Now watch this scale down here. This is infrared light, and then it moves into the microwave light. Then we increase the contrast so we can start to see the variation in the amount of microwave light. So backing this up again, I want to point out one more time that we're looking at different kinds of light. Here's visible light to begin with, and as we move this scale, we move into the infrared, and then we move into the microwave wavelength of light. If we then increase the contrast in our detector, we can see the differences in the amount of microwave radiation in different areas. The reason this picture has this red band across the middle of it is that this is the microwave light given off by the Milky Way surrounding us. So we're like in the center of this thing looking out. And of course, we're going to see more microwave light in the Milky Way because of all the sources of energy that are found in the Milky Way, all the different stars and nebulae and so forth. And so they can also adjust this image to remove this band of red light and see beyond the Milky Way. And that's what they'd done in the first photo that we looked at, which was this one. They've removed the interference from the Milky Way. Okay, so now we're going to look at another video. This one's going to go in the opposite direction. The first video we looked at went from the Earth and zoomed out to the sun, the solar system, the Milky Way, out beyond the galaxies, and we ended up seeing the CMB, the cosmic microwave background. This one's going to go the opposite direction, which means this one's going to go forward in time from the Big Bang to the present. The first one, zooming out from ourselves, we were going back in time. This one, we're going to turn it around, basically play it backwards. So here's the cosmic microwave background to begin with the variations in the amount of matter and energy. We're going to zoom into this one little portion, and we're going to see these clouds of matter and energy condensing and collapsing on themselves to gradually form galaxies that ignite, and now they're quasars, early young galaxies. And then as the quasars age, they may become galaxies that are more like what we're used to looking at. And then these galaxies form stars and planets and people that send satellites out into space. So this diagram at the end here is basically a timeline of history of the universe, starting with the cosmic microwave background up to the formation of the quasars. They're aging into galaxies. Our galaxy probably formed about here, 4.5 billion years ago. Well, not our galaxy, excuse me, our solar system. The sun and the earth are about this old for this whole thing. Our galaxy probably formed about here, the Milky Way, about 12 billion years ago. Okay, so let's look at another approach to this. The universe fingerprint is the idea that if we make computer simulations, we can adjust the various components of the code in the simulation to try to make sure that our simulation matches the measurements made by the WMAP satellite. And that limits the possible conditions of the universe. We adjust the conditions in our computer simulations until they match. If they don't match, we have to toss out those simulations. We want the simulation that gives the best match for the data. And so that's why they're comparing this to a fingerprint, because it's unique to the conditions of our universe. So here's the WMAP probe, here's the cosmic microwave background, and we're going to metaphorically compare it to a fingerprint. If we look here, we see that there are all of these possible universal conditions. So some simulations resulted in a universe like this. Others resulted in this one. Others resulted in this one and this one. Well, this is what we have actually measured our universe to look like. And these ones don't match these conditions. They don't match the data. So we're going to erase all of the possible universal simulations that don't match. Oh, I'm sorry. I went forward. We're going to erase all the ones that don't match and only keep the one that matches the data that we've measured. There's the data. That's our fingerprint. All of these are possible fingerprints. Only one of them matches. Well, what were the conditions of this one that actually matched? Here they are. If we change any of these assumptions, any of these conditions in our computer model, then they don't match what we actually measure. The age of the universe must be this amount with this shape, this much dark matter, and so forth, in order to come up with a computer simulation that matches what we observe in reality. All those other computer simulations modified the age of the first stars and the clumpiness of the universe. They changed those and it didn't match reality. So this is our best computer simulation of what the universe is like. Here's another one. We're going to once again attempt to match what we've observed with some possible ideas of what could have happened. So just like a pebble is going to create a certain pattern of ripples in a pond, the specific distribution of matter and energy in the early universe has left a specific pattern of ripples across the cosmic microwave background. So by looking at that specific pattern of ripples, we can compare that to the pond that would correctly give us that distribution of ripples, that pattern in nature. So here we have two ponds, and you can tell they look a little different, and that's because they're made of different materials. It's like space and time are made of different things in these two ponds. So which one best matches what we see today? Well, drop a stone in, we see different kinds of ripples in the different materials. And it turns out that the pond on the right is more like the ripples that we see around us, but not just one stone, lots of stones falling in there, creating a whole chaotic pattern of ripples, which then we can match to different portions of the cosmic microwave background, which in this case is including the Milky Way in the image. So here we have these theories, we have this data, we have these different explanations. I just want to review a couple things about how a scientist approaches this kind of information. So a scientific theory is a really powerful explanation of many facts. It explains the fact. It's not just a fact itself, it's an explanation of the facts. It's beyond the facts, bigger than the facts. And any good theory leads to testable predictions. So we're going to be testing the theory. We're not just going to accept it up front. We're going to continue to test it. We're going to use it to make predictions. Then we're going to try to find out if those predictions hold up. And the theory has to fit the data. If we get new data, we either have to modify the theory, improving it, or we have to toss it out. If we can't make the theory fit the data, we're going to throw it away. If we can modify it, if we can tweak it, if we can improve it, then we'll keep it, but we're going to change it from the original ideas. This has been done with the Big Bang to include a time that they call inflation. The original theory did not include this inflationary era, but now the new Big Bang theory does include inflation. So any cosmological explanation of the universe has to include the facts. It has to include the redshift of galaxies moving away from us. It has to include the pattern of the cosmic microwave background surrounding us. All these facts must be included in our cosmological explanation. The best explanation for these two things is the Big Bang. It fits the major pieces of data. Not only that, it also fits with calculations that are based on Einstein's theory of general relativity. So this is where the Big Bang came from. This is what the idea is telling us and how it fits with reality of what we're able to measure around us. Of course, there are lots of details to work out still. In particular, what's going to happen to the universe in the future. But not knowing everything is really what makes it interesting. Here's a timeline of the evolution of the universe, where the Big Bang happened at the beginning. Here's time along the side. Notice this is not an even scale. This is 1 second. It took 1 second for all of this to occur. But this is 15 billion years, 15,000 million. So it's not an even scale for time across the bottom. Excuse me, across the top. Across the bottom, we have temperature. And you can see the temperature is going down from 10 to the 32nd degrees. 10 with 32 zeros behind it. That's how hot the early universe was. And it's gradually cooling and then quickly cooling down to only 3 degrees today. Now, this is a huge number, the temperature, but the time is a tiny number, 10 to the negative 43rd seconds. That's 1 over 10 with 43 zeros behind it. 1 divided by 10 with 43 zeros, a tiny fraction of a second. One thing I'll point out here is that we see the universe expanding from the Big Bang and a sudden increase in the speed of expansion. That's what I was talking about with inflation. We think that at this point in time, the universe rapidly expanded from smaller than an atom to bigger than a football at this time. And then it's continued expanding ever since. So in here, we're seeing matter separate out from energy. In here, we're seeing protons and neutrons forming from the quarks of the earlier time. Protons and neutrons and joining together with electrons to form atoms. And that all took this amount of time. And this is about when the cosmic microwave background would have been emitted. And then we see the galaxies forming. Within them, the stars are forming, and of course, humans forming. So next time, we're going to pick up and look at all these events during the universe's lifetime, the evolution of the universe. And we're going to finish that by looking at some of the possible endings of the universe. Again, we're not sure which of those endings is going to happen, but we're going to look at these details of these events that happened since the Big Bang. We're going to look at those a little more closely next time. And so that's all I have for you today. I thank you for joining us and for sticking with me, and I hope you have a great day. Kaboom!